Okay, we want to prove a small supplement to the closed subgroup theorem. So we are in the situation that we have a closed subgroup of a Lie group G. And by the closed subgroup theorem, the H is a Lie subgroup, so it has its own Lie algebra, and we assume that we have a vector space complement to this Lie algebra in the large Lie algebra. And the claim is there exists a zero neighborhood such that the map phi, here underlined green, on the zero neighborhood times the subgroup is a diffeomorphism onto one of these product sets where we exponentiate the zero neighborhood with respect to the Lie group exponential of the large group and then multiply with elements in H. And so this is the claim is that this is a diffeomorphism onto an open subset. And this is quite different from the usual things we do because, I mean, what um, we know that there is a zero neighborhood in the subspace E, an open zero neighborhood, and an open zero neighborhood in the Lie subalgebra, such that, well, if I exponentiate with the large Lie group exponential, the Cartesian product, um, then and intersect it later with H, sorry, yes, Cartesian product of the intersection, then this is the same as the Lie group exponential of the small Lie group, and I'm just exponentiating the UH. Further, we can shrink all the sets such that xg is a diffeomorphism on the Cartesian product, right? And we note that xg of ue, if we intersect this with h, this is only the trivial intersection, namely it's the identity element which lies in the intersection. Okay, great. So this is what we have been doing before. We basically build Cartesian products on which the x restricts nicely. Well, um, let's consider also an auxiliary map and see how we can use this to actually get to the neighborhoods we want. So the auxiliary map is called psi, and it will be defined on UE times the exponentiated subset UH. I mean, instead of xg, I could have also written, so this is inside of H, gets exponentiated into H, and I want to view this as a map to G. What it does, it takes the element in the first component, exponentiates it, and multiplies it with the H. So this is this auxiliary map is, after shrinking UE and UH, a diffeomorphism onto an open set. This works, or the argument for this works like the proof for coordinates of the second kind. Okay, so we have this diffeomorphism, and now by continuity of multiplication in the Lie group, we can pick an open zero neighborhood, VE, which is symmetric in the sense that if I take if I multiply with -1 and look at the things, I get the same set. And this is inside of UE and it's open, such that the following happens. If I exponentiate with respect to G the VE, and I exponentiate again with respect to the VE, this is contained in psi of UE times xg(UH). And I mean, if we want, we can write this, of course, differently. We can write this xg of UE times multiplied with xg of UH. right? So this is the thing on the right-hand side by virtue of psi being a diffeomorphism in open subset, and we can basically force these products to be in there by choosing VE to be small enough. Okay, we claim now that the map phi xh gets sent to exp gx times h is a diffeomorphism onto an open set if defined on this set VE times h we were considering. Okay, so let's take a look how this works. Um, okay, let us note first that if I have phi and I apply this to a product of two things, then I get here xgx. But from the right-hand side, I just multiply. So this is right translation of phi of x h1. So I can pull out stuff with right multiplication, and this is useful um, since a quick calculation shows that if I take the tangent map at any point x and but with the identity element of this phi, so here the identity element at h, then this turns out to be just the tangent map at the point x0 of my map exp g. But now let's recap a little bit. So the x comes from the open set VE. The open set VE is contained in UE, and we have basically constructed the UE in such a way that the X is a diffeomorphism on this Cartesian product. So we are in the first component, we're inside of this one. In the second component, we are now, because we have 0, so we are inside of this set UH. So we know that this one is a diffeomorphism, or actually it's a linear isomorphism. Maybe that I should have said. But now, so it's a diffeomorphism, or I should have said is invertible. Oops, what happened now? Is invertible. Okay, but now, well, if I want to compute at any other point, okay, let's not call it G, let's call it H, at any other point the differential, then by my formula, I see that this is the differential at the point X, and then you have here the identity element of the phi, which we already know is invertible. And well, since this formula with the right multiplication, then we have here the tangent map of the right multiplication with the element h. And these guys are also invertible because on a Lie group, the right multiplications with fixed elements are diffeomorphisms on the Lie group. So uh, we see that txh phi is invertible as a composition of invertible linear mappings. So this holds for all xh in VE times h, and this is a nice little trick here. So what we know now, so phi is a local diffeomorphism by the inverse function theorem. Okay, and it will be a diffeomorphism if we can prove that it is injective, right? Because this is something we cannot guarantee by the inverse function theorem alone. So we need an additional argument for this. Okay. So let us assume that phi of x h is actually the same as phi of x prime h prime. Yeah, so and let's see what this brings to the table. Um, okay, so okay, what is this? This is exp uh, g of x times h, and this is exp g of x prime times h prime. Okay, so sorting things out, what we get is x of gx inverse times x g of x prime has to be equal to h times h prime inverse. Okay, and now we see here that the left-hand side, since the x's are, so this is in exp VE times exp VE, well, just by construction, because the x's are from VE. The right-hand side, since H is a subgroup, this comes from H. So we see that this is in the intersection of H with exp G VE. Well, let's write square here for the two-time thing. Okay, and now what we see here. Okay, let's recap. What was this product contained in? Basically, we had a condition on the product. We said we wanted to choose them like this, that the product is contained in this set over here in exp of UE times exp of UH. Okay, so let's see. So this is and contained in exp of UE exp of UH. Again, coordinates of the second time. We know that the exp here is essentially is injective on this thing, and so we have this, and now we intersect it with H. And okay, so so if we intersect this set here with H, let's see what condition we had on this. Aha. So we see that if we have exp of the UE times UH and we intersect this with H, it's the same as exp applied to the UH. So what we see here is basically if we intersect this set, the exp UE times exp UH with the H, this stuff is contained in exp G of the UH. Okay. So in other words, exp of exp G of X is sorry, of X prime is contained. I mean, if we're just rearranging the equation upstairs here, where we have the product of the two things, we are flipping again over the inverse from the left-hand side. So this is inside of exp G X multiplied with exp G of UH. But okay, if now looking at the whole thing, where we have where we build our auxiliary map, so we this is exactly since we have UE and UH or exp of UH, where this is exactly in the image of our auxiliary map psi. Yeah, so this is in the image of psi, since psi was injective. What we get here is we must have that x is equal to x prime, right? Because both x and x prime are coming from this subset UE here. And basically by construction of these sets, uh, since psi is injective, we have no choice. X needs to be equal to x prime. And well, now let's take a look what we have if x of x is equal to if x is equal to x prime, we see that the left-hand side of this equation, which we have here in yellow, needs to be the identity. So in other words, this also proves that h needs to be the same as h prime, basically because h times h prime inverse is equal to the identity. And so we get injectivity of the map phi. And this finishes the proof. So phi is now a diffeomorphism as claimed.